Every single second, the global digital infrastructure is pushed closer to a physical breaking point. We're generating data at a scale that overwhelms our hardware. For decades, enterprise architecture relied on traditional business intelligence. In this model, clean, highly structured data flowed into a single, centralized relational database, where it could be queried at a predictable pace. This model collapses under the weight of the modern digital economy. High-frequency trading logs, billions of IoT sensor readings, and continuous social media streams create a relentless influx. Funneling this into a centralized database creates a fatal bottleneck. Standard procedures move data over a network to static processing code. But when datasets become too massive to transport, the architecture must invert. To process big data, we leave the mass where it sits and move lightweight processing code directly to the data. Digital data is categorized by simply producing information. We are now accumulating raw data at a scale that requires new systems to manage. Extracting value from this mass requires a total reconfiguration of how we build and interact with digital infrastructure. Unit 1 provides the framework to process exabyte-scale data. First, we classify the dataset's dimensions using the 6 V's. Second, we address the hardware foundation by implementing distributed file systems. Third, we apply a rigorous data science methodology to extract actionable insights. To survive this influx, organizations must master both the physical distributed infrastructure and the mathematical methodologies that run on top of it. Digital data is categorized by its level of organization. Structured data fits into the rigid rows and columns of a relational database. Semi-structured data, like HTML or XML, contains some organizational tags. But the final category, unstructured data, lacks a predefined model entirely. This node map in Figure 1.8 illustrates the reality of modern enterprise operations. The majority of our data, emails, images, audio files, and social media posts, completely lacks an internal schema. Unstructured formats constitute approximately 80% of all data generated in a modern enterprise. This creates a severe operational challenge. Because there is no rigid schema to define the data, standard SQL queries cannot read it. You cannot ask a traditional database to summarize the emotional sentiment of 10,000 customer service audio logs. The most valuable operational insights are buried inside these dense, hard-to-read formats. Accessing that value forces us to build systems that can process data without relying on rigid schemas. To measure this complexity, we use the 6 V's, the definitive metrics that characterize data as big data. This framework proves that big data is a multi-dimensional scaling problem, not just a storage issue. The first axis is volume, representing the shift from gigabytes into zettabytes and exabytes. The second is velocity. Data degrades in value quickly. If delivery and processing are not real-time, the information is often useless by the time it reaches an analyst. Next is variety, addressing the unstructured mix of XML, video, and text. This is compounded by variability. Data flow is rarely consistent. A system must handle massive, unpredictable traffic spikes without crashing. Finally, veracity measures the accuracy of the data and the constant effort to filter out noise and bias. All of this culminates in value, the ultimate goal of converting raw inputs into actionable strategy. A modern data architecture must endure the pressure of all 6 metrics simultaneously. If it fails on even one, the entire ecosystem collapses.
To solve the volume problem, engineers initially tried vertical scaling, buying larger, more expensive supercomputers. But physics and budget constraints eventually make it impossible to build a single machine big enough for modern loads. The solution is horizontal scaling. Instead of building one massive brain, we network thousands of standard commodity computers to operate as a single massive cluster. To store data across this cluster, we use a distributed file system. When a massive dataset arrives, the system chops it into small blocks and scatters them across the thousands of linked nodes. Managing this grid requires a coordinator. Hadoop Yarn serves as the cluster's traffic cop. It manages resource allocation across the grid, scheduling tasks and ensuring multiple workloads can run concurrently without colliding. This relies on a shared nothing architecture. Every node has its own memory and disk, operating independently. If one node fails, the rest of the cluster continues processing without interruption, ensuring high availability. By scattering data across a massive grid, the distributed file system solves the fundamental physical limitation of big data. It brings the processing power directly to where the data lives. Storing data is not the same as understanding it. This pyramid diagram in Figure 3.1 shows the required conversion. Moving from raw data to actionable insights requires a strict analytical engine, the data science process. The pipeline begins with problem definition, identifying a specific goal, like a retail company aiming to understand customer purchase patterns. Step 2 is data collection, where the relevant logs and transaction histories are gathered from the cluster. Raw data is notoriously noisy. Step 3 is data cleaning and pre-processing. In our retail example, this involves identifying and removing duplicate customer records so the subsequent analysis isn't skewed by garbage data. Only then can analysts move to Step 4, exploratory data analysis. This is where statistical summaries reveal hidden correlations, like discovering that customers who buy product A are statistically likely to also purchase product B. Those insights feed Step 5, modeling and analysis. Data scientists deploy machine learning algorithms against the prepared datasets, training models to predict future events, such as calculating the exact likelihood of customer churn. Finally, Step 6 is evaluation and deployment. The trained predictive model is pushed into the real-world environment to begin making automated real-time decisions for the enterprise. Without the rigorous execution of this 6-step methodology, a distributed data lake is nothing more than an expensive dumping ground for unstructured noise. This flowchart illustrates the complete life cycle. The 6 V's are stabilized by the distributed hardware of the node grid, which is then decoded by the precise software gears of the data science pipeline. The ultimate law of this ecosystem is logical. Higher volumes of data yield more accurate analysis. More accurate analysis yields greater confidence in operational decision-making. Mastering this pipeline converts raw noise into a high-fidelity model of organizational behavior. It turns a crushing liability into an organization's most valuable predictive asset. Now that the macro architecture is established, Unit 2 will zoom in on the specific tools of the trade, detailing how data lakes, NoSQL databases, and ETL pipelines execute these theories in practice. Processing at the exabyte scale defines the modern standard for competitive advantage. It is the technical engine that separates market leaders from their competitors.
For decades, data infrastructure relied on a single, highly structured assumption. Information arrives neatly formatted and gets stored on a central server. But when that same server is simultaneously hit with high-definition video streams, scattered JSON files, and continuous sensor logs, the hardware reaches its physical limit. The traditional method relies on formatting data before it is stored, a concept known as schema on write. Modern data makes this impossible. The sheer volume, the variety of formats, and the velocity of the incoming streams create a bottleneck that crashes legacy databases. To process information at the petabyte scale, we must replace legacy systems with distributed models designed to handle high-velocity ingestion. We will build this architecture in 4 distinct phases: identifying the exact sources of our incoming data, constructing scalable repositories to hold it, engineering pipelines to move it, and installing the processing engines to analyze it. Surviving modern data loads requires a shift from rigid relational rows and columns to flexible, horizontally scaled ecosystems. We start at the perimeter with the incoming data. Historically, this was strictly structured data, organized information with defined lengths and formats that fit into traditional database tables. Today, structured data is a minority. The vast majority of incoming information is semi-structured, like XML or JSON files, or unstructured, ranging from raw text logs to image and video files. To capture this diverse information, a big data ecosystem uses specific entry points called service bindings. These act as the critical connectors, pulling disparate external sources into our internal storage platforms. We collect this data across 5 distinct vectors. Web APIs gather information from social media and financial markets. IoT middleware ingests continuous streams from physical sensors. Enterprise systems export data from existing CRM software. Cloud platforms offer storage services, and streaming connectors integrate real-time databases.
Because this information arrives from 5 vectors in unstructured formats, forcing it into a predefined schema at the front door would immediately halt ingestion. We need a storage paradigm that accepts the data in its native state. Before storing this data, we must solve the physical scaling problem. Traditional relational database management systems rely on vertical scaling. When the database fills up, the only solution is to buy a larger, more expensive central CPU. Big data solves this through horizontal scaling. Instead of buying one massive supercomputer, the system connects hundreds of cheap commodity servers into a distributed grid. This comparison outlines the stark differences. Vertical scaling hits high hardware costs. Horizontal scaling allows adding nodes on demand. Crucially, the scaling type dictates the data model. Vertically scaled databases demands rigid schemas, while horizontal systems allow flexible schemas for unstructured data. This architectural split creates 2 distinct repositories. The traditional data warehouse remains useful for structured, integrated data that is already optimized for specific business intelligence queries. But the core repository of the modern ecosystem is the data lake. The data lake is a centralized storage system that accepts vast amounts of raw data in its native format. It scales horizontally and uses a schema-on-read approach, applying structure only when the data is eventually queried. To manage the specific files resting within that lake, we deploy NoSQL databases, like MongoDB or Cassandra. These non-relational tools are built to organize large volumes of document and key value stores without forcing them into tables. Data lakes and horizontal scaling solve our storage constraints. However, moving millions of raw files from the service bindings into the lake requires us to rewire how data flows through our infrastructure. We bridge the gap between collection and storage using data pipelines. These are automated workflows that dictate exactly how data moves through the architecture. The legacy approach is ETL: extract the data, transform it to fit a specific schema, and then load it into the warehouse. When dealing with petabytes of streaming data, transforming everything before saving it creates an immense computational bottleneck. This diagram illustrates the modern solution, ELT. We extract the data, immediately load it raw into the data lake, and transform it only when analysis is required. Loading first preserves the original information, allowing analysts to transform subsets on demand without bottlenecks. This breakdown outlines the pipeline sequence. It begins with data ingestion, moves into data storage across distributed nodes, and proceeds to data processing. Only after those steps do we execute data analysis and visualization. The flow is secured by strict data governance protocols. By reversing the traditional pipeline into an ELT model, the system strategically delays the heavy computational load of data transformation until the exact moment a user requests an analysis. We have now stored our raw data in a distributed layer, typically utilizing the Hadoop Distributed File System, or HDFS. But retrieving that data traditionally requires writing complex Java MapReduce code, a skill set far beyond standard data analysts. To solve this, we install a processing engine called Apache Hive. Hive sits on top of Hadoop and allows users to query the unstructured data lake using a familiar SQL-like language known as HiveQL. This flowchart maps the query's path. A user enters a HiveQL command into the UI. The driver receives it, passing it to the compiler, then the execution engine. The execution engine translates the simple query into MapReduce tasks, executing them across distributed Hadoop clusters. Hive eliminates the need for analysts to write complex Java code. It places the parallel processing power of a Hadoop cluster directly into the hands of standard business intelligence teams. We have now constructed a complete functional big data ecosystem. We addressed the challenge of data variety by establishing distinct service bindings to capture diverse file types from APIs and IoT sensors. We solved the challenge of data volume by implementing ELT pipelines, allowing us to dump data rapidly into horizontally scalable data links. Finally, we made this raw, unstructured chaos actionable by deploying processing engines like Hive, translating massive distributed workloads into readable business intelligence. Modern data architecture functions as a modular ecosystem where storage, processing, and querying are distributed across distinct, specialized layers. With the hardware and pipelines successfully mapped, the physical architecture is complete. The next operational challenge is ensuring the quality of the data flowing through these pipes. and building complex data models to extract predictive insights. Understanding the construction of the warehouse is a prerequisite to organizing the inventory. Now that the ecosystem is built, we are ready to put the data to work.
There is a specific throughput limit where traditional software engineering hits a point of failure. When information reaches a certain velocity and volume, legacy database architectures cannot sustain the load. For decades, the baseline standard has been the Relational Database Management System, or RDBMS. These systems rely on highly structured tables and rigid predefined schemas, designed for enterprise environments where data is measured in neat, manageable gigabytes. When an RDBMS needs more capacity, engineers rely on vertical scaling. This involves upgrading a single centralized server by adding more CPU cores and RAM to the existing motherboard. However, a single machine is bound by its physical motherboard slots and bus speeds. At petabyte scales, the ingestion of unstructured real-time data exceeds the hardware capacity of any one server. Modern information flows quickly outgrew these hardware constraints. Reaching this physical limit forced engineers to move away from single-server relational systems and design a different architecture. The engineering solution to these hardware limits is the Big Data Management System, built on the NoSQL model. Instead of relying on one massive server, NoSQL utilizes horizontal scalability. This distributes the storage and processing load across a cluster of hundreds of commodity machines working in parallel. Operating at this scale involves schema on read. The system ingests massive amounts of raw, unstructured data immediately, applying a structural schema only when a specific query is executed. This table outlines the distinctions. RDBMSs are categorized as relational and vertically scalable. NoSQL databases are non-relational and scale horizontally. The trade-off is how users interrogate them. SQL executes complex multi-layered queries, while NoSQL schemas lack deep relational power. Moving away from the structural safety of rigid SQL tables is the price for a system that can ingest petabytes of varied data in real time. To organize this distributed information, engineers use data modeling. This is the architectural blueprint defining how data elements are stored, connected, and accessed across a system. This text shows the legacy models. Early systems used hierarchical, parent-child trees, or network structures. The relational era introduced the entity relationship model, linking entities like a customer to an order, as well as object-oriented models. Modern big data architecture accommodates varied file formats. While tabular data might use a simple CSV structure, web applications rely on JSON, a text-based format suited for transmitting semi-structured data. In platforms like MongoDB, this evolves into document databases. As detailed here, MongoDB converts JSON into a binary format called BSON. Storing nested data in a single schemaless document removes the need for processor-heavy table joins to retrieve related info. For datasets defined by dense interconnections, like social media platforms, engineers deploy graph-based databases. This overview highlights the unique architecture. Graph databases store entities as nodes, and the connections between them as links. This design outputs real-time query results for complex networks, allowing administrators to update relationships without significant schema alterations. Modern big data models prioritize the agility of network relationships and nested objects over the strict tabular rows of legacy environments. Operating without rigid SQL schemas presents an operational risk. Without active management, a flexible distributed data lake can degrade into an unsearchable data swamp. Organizations implement big data management techniques to maintain order across clusters. The foundational layer is data governance, ensuring data is used consistently. Further down, data quality management scrubs inaccuracies, while data security protects repositories from unauthorized access and loss. Once the pipeline is secure, it yields the final outputs. Big data analytics extracts hidden patterns from the repository, while predictive analytics applies machine learning to forecast future demand. Extracting truth from chaos requires the continuous engineering of a managed pipeline. High-velocity healthcare environments provide a clear test case for these distributed systems. Consider near-patient IoT medical sensors. they constantly stream a high-velocity feed of unstructured vitals, like continuous heart rate readings, directly into a cluster. As outlined in paragraph 7, the big data system analyzes this telemetry in real time. If a physiological parameter crosses a safety limit, the system triggers an alarm, alerting a doctor to take immediate action.
A traditional SQL database attempting to batch process this telemetry would introduce fatal latency. Only the velocity of a distributed big data architecture allows for these life-saving alerts. This architecture is equally critical for handling extreme data volume, such as the macro-scale inputs generated by the energy sector. Look at paragraph 9. Smart electric meters record power consumption every 15 minutes. Across an entire city, this generates millions of continuous data points streaming into centralized servers. The management pipeline analyzes this volume to forecast citywide power loads. It then issues recommendations to industrial manufacturers on when to run their heavy machinery to avoid straining the local grid. Moving from rigid tables to dynamic, managed pipelines marks the transition from simple record-keeping to a system capable of forecasting the future.
Modern enterprise systems capture billions of data points every second. Yet, for most organizations, the expected return on this information fails to materialize. Scaling up storage capacity to handle massive volume, velocity, and variety does not yield intelligence. It simply yields a larger archive. Raw data is inherently disorganized, and without a structured mechanism to filter and evaluate it, the information remains unusable. Translating that raw noise into actionable intelligence requires a specific architectural framework. As outlined here in Unit 4, the solution is the construction of a big data processing pipeline. This pipeline is an integrated multi-stage computing solution. It is engineered specifically to ingest, process, and analyze petabyte-scale data, operating in either continuous real-time streams or scheduled batch modes. The difference between a company that hoards digital noise and one that engineers business intelligence comes down entirely to how efficiently they build and maintain this architecture. To understand how this works, we have to build the pipeline block by block, starting at the boundary between the external world and internal infrastructure: data ingestion. Ingestion is the strictly defined process of collecting varied, unstructured data from external sources and bringing it securely into the pipeline. This text explains ingestion relies heavily on service bindings. These specific connectors allow systems to identify, register, and pull data. Social media or financial data is accessed via web APIs, while sensor data relies on IoT middleware and service gateways. Once data crosses the threshold, it must land immediately in a data storage layer. Traditional databases quickly overwhelm under this throughput. To handle petabyte-scale influxes, organizations implement distributed storage systems like the Hadoop file system or massive cloud buckets. This storage layer optimizes high-efficiency data query and retrieval, ensuring that the heavy computational engines further down the pipeline are never starved for inputs. If ingestion connectors fail to capture data or the storage layer bottlenecks its retrieval, the pipeline chokes before the analytics layer even registers an event. With the raw material secured, we pull it from storage into the data processing layer. Processing is the computational heavy lifting required to clean, filter, and transform messy, disparate datasets into a standardized format. Algorithms perform vital aggregation operations. They remove redundant duplicates, extract the specific features needed, and perform imputation, the statistical estimation and insertion of missing values, to ensure the dataset is mathematically complete. It is vital to note that processing only makes the data usable. It does not generate insights. The polished data is then fed into the data analysis layer, the mathematical engines of the pipeline. This document clearly separates the two functions. Step 3 cleans and transforms raw data to make it usable. Step 4 takes that usable data and applies statistical methods and machine learning. The analysis layer is where hidden correlations are unearthed, and actual predictions and decision-making support are finally generated. Together, these two blocks form the engine room, where raw, historical bytes are officially converted into high-value intellectual property. The final sequential step in the process is data visualization. Complex machine learning outputs must be translated into accessible charts and dashboards for business leaders. But these 5 steps don't execute in isolation. They are driven by an overarching control plane, Data orchestration. Orchestration schedules tasks, coordinates data movement, and ensures resources are allocated in the exact correct sequence. Finally, the entire pipeline sits on the foundational layer of data governance and security. As this text dictates, governance ensures the data remains accurate, mathematically consistent, and strictly compliant with privacy regulations at every single transition point in the system. If workflows require manual intervention or data exposes the company to legal vulnerabilities, the most advanced analytical model in the world becomes a liability. We now have a complete 7-part architectural pipeline operating continuously at scale. Massive chaotic inputs are drawn through service bindings, secured in scalable storage, systematically cleaned, mathematically analyzed, and finally rendered as visual insights. Mastering the mechanics of this flow is the primary requirement for understanding modern big data integration.
Specific database brands, analytic tools, and programming languages will constantly evolve, but this core functional blueprint, the sequence of operations, remains the standard architecture across the industry. The practice of data engineering is defined by the architecture of this resilient, automated pipeline, the system that brings mathematical algorithms to